The question that I have is, could you go over a 3D example on finding support reactions? And in this particular example, I will solve the problem using both the scalar and the vector methods. Let's go ahead and do this example. We have a horizontal plate, a rectangular plate with a weight of 500 pounds being supported by 3 vertical cables. A point load of 200 pounds is acting at this point. Question is to find the tensions in the cables. It's easy to see that the body to be analyzed here is the plate. So here's the free body diagram of the plate. The weight of 500 pounds is acting at the centroid of this rectangular plate, which is right in the middle. The tensions in the cables are acting vertically up. I will call them as TA, TB, and TC. We'll use the scalar method. The unknowns of the problem are TA, TB, and TC, right? So there are 3 of them, but we know we have 6 equations available to us. So obviously we don't need all 6 of them. So we're going to have to use whatever we need in order to solve these unknowns. Remember we said we can take moments about either the axes of the coordinate system or lines that are parallel to the axes, right? So what I'm doing here is I'm defining a line, an axis that is parallel to the x-axis, okay, but it passes through this edge of the plate, okay, and the direction of that axis is in the same direction as this x-axis. Now I'm going to write down a moment equation about this axis in the counterclockwise direction, all right. So I see that TC is on that axis, TA is on that axis, 200 pounds is on that axis, so all 3 of these forces will not make a contribution to this equation. So only forces that will make a contribution are TB and 500 pounds, right? This is the line of action of the weight 500 pounds, and the perpendicular distance to that from my x prime axis is this distance, which is 1.5 feet. And this is also giving me a counterclockwise moment, so that goes in as a positive term in this equation. And you can see TB is going to give me a clockwise moment, so that goes in as a negative term. And the perpendicular distance to the line of action of that is 3 feet, right? So TB multiplied by 3 feet goes in as a negative moment in that equation. So TB is the only unknown in that equation, and therefore TB can be solved for right away, and TB is calculated to be 250 pounds. Now I'm going to write down a moment equation about the y-axis, all right? So this 500 pounds and 200 pounds are both acting vertically down, and they both have the same perpendicular distance from this axis, right? So I have grouped them over here, 500 plus 200 multiplied by 2 feet. The moment due to these forces is a counterclockwise moment, so they go in as a positive term in that equation. The tensions TB and TC are both going to give me a clockwise moment. The perpendicular distance to them are also equal, and they are just 4 feet, right? So here I have a minus TB times 4 to account for this force, and here I have a minus TC multiplied by 4 to account for this force. Noting that we have a value for TB, this equation needs a value of 100 pounds for TC. My final equation is a force equation in the z direction. We note that all of the forces acting on this plate are actually in the z direction. So we sum them up algebraically. So here's my equation. We already know TC and TB, and substitute these numbers in here, and I get a value of 350 pounds for TA. So that's it, we are done. We found all 3 tensions. Just to re-emphasize, let's note that we only had to use 3 of the 6 available equilibrium equations to solve this problem, because there are only 3 unknowns in this problem. My second comment is, just as in 2D problems, I could have used different combinations of equations to solve this problem. For example, instead of this last equation, which is a force equation, right, I could have used this moment equation to find a value for TA. So what I did here is I wrote down a moment equation about the y prime axis, and this is that equation. That gives me the same value of 350 pounds for TA. So I want to solve this problem using the vector method. Let's go ahead and list the steps here. So what we do is, we take each of the forces acting on this plate and express each of them as a three-dimensional Cartesian vector. The equilibrium force equation then is sum of the force vectors equals 0. We do the same thing for the moments. First we take all of the forces and find the moments of each of these forces about a common point, say point O, as a vector. Then we take all the moments acting on the body and express them as vectors. Of course, in this problem, we don't have any moment. They're all forces. Alright, so once you have expressed the moments of forces and the moments as vectors, then the equilibrium moment equation is simply sum of the vector moments of each of these different components is 0. Now remember, this is a vector equation, right? So there are actually three independent equations built into it. And similarly, this is a vector equation, so there are three equations in there. So we have a total of 6 equations again. So in the final phase, both the scalar method and the vector method leads to the same 6 equations. So here are the vectors of each of the 5 forces. We note that each of the 5 forces has only one component, which is the component in the z direction, right? So to find the force vectors, all we have to do is to take the magnitude of each of these forces, right, which are TA, TB, TC, 500 and 200, and multiply them with the unit vectors in the z direction. So which will be k for that, k for that, k for that, but minus k and minus k for these two because they are acting in the direction opposite to the positive z-axis. Now we sum up the force vectors and set it to 0. So if this vector is to be 0, its magnitude must be equal to 0, and therefore this quantity is 0. So this is my first equation here, and I immediately note that this equation is identical to equation 3 of the scalar method. Now let's go ahead and write the moment equilibrium equation. If you recall, moment of a force about point O is given by this equation, right? MO, vector MO equals vector R cross vector F, right? So here vector R is any vector going from point O to any point on the line of action of the force F. And of course vector F is the vector representing the force. So we have 5 forces here, so we're going to end up with 5 of these, and we sum them up, right, and set it to 0. So that's our vector moment equation. But of course, to expand and go further, we need the r vectors and the f vectors, right? So we already have the f vectors, so we only have to find the r vectors. So they're all here. These r vectors are all going from the origin of the coordinate system O. Therefore, all we need to do is to find the coordinates of the point that the r vectors are going to, and then we can write down the r vector simply using the components of the coordinates of that point, right? So you can see point A lies on the y-axis, and therefore its coordinate is 0 in the x direction, 3 in the y direction, 0 in the z direction, right? So vector RA, which is the vector going like this from O to A, right, is simply 3 times j. The coordinates of point B are 4 in the x direction, 0 in the y direction, 0 in the z direction, and therefore RB, vector RB is simply 4 times I. Coordinates of point C are 4 in the x direction, 3 in the y direction, 0 in the z direction, right? And therefore vector RC is 4i plus 3j, and so on. I'll let you follow these two on your own. Now that we have the f vectors and the r vectors, we can go ahead and expand these cross products. We'll use the determinant method for that. So let's go ahead and do one of them here. Remember what we do, right? The first row contains the unit vectors I, j, and k. That's the case in all of these cross products. The second row contains the components of the r vector. So for example, RA has 0 in the I direction, 3 in the j direction, and 0 in the k direction, right? So I have 0, 3, and 0 in the second row. The third row has the components of the F vector, the force vector, right? So we can see all of these force vectors have only the kth component, and therefore all of them will have zeros in the first two locations, and only the third location will have a number on the third row. So for vector TA, the magnitude is simply T sub A. So I'll let you go ahead and verify these four on your own. If you want to write down all of the steps, there would be a step here involving 2 by 2 determinants, right? Because there are lots of zeros here, I was able to skip that step and write this directly. So this quantity goes with this goes with that, this goes with this goes with this, and this goes with this. If it's difficult for you to follow, go ahead and write the intermediate step and then go to this step. So once again, here's the last step that I had in the previous slide. Now I'm going to group the terms like this. Take all of the I terms and put them in here. Take all the j terms and put them in here. And there are no k terms, so the k term has a 0 coefficient. So math tells you that this vector is to be 0, then each of the components must be individually 0. So this equals 0 and this equals 0. Again, I copied the first equation from the previous slide. So now we got three equations, right? This, and this. We know there are three unknowns, T sub A, T sub B, T sub C. So we can solve these equations. Remember previously we noted that this equation number 1 is the same equation as the one that we got in the scalar method, right? The last equation, right? Then you would tend to think that the first equation should be identical to these two, right? But they are not. The reason they are not is because, remember, there are multiple ways to take moments, right? In the scalar method, I took the moment about the x prime axis, right? So we ended up this equation. This is equation number 1 of the scalar method. Had I taken that equation from the x-axis instead of the x prime axis, this is what I would get. This is the moment term associated with the force TA. TA has a perpendicular distance of 3 feet and TC has a perpendicular distance of 3 feet. Both of these give us a counterclockwise moment, so they go in as positive terms. And then this 500 pounds as a perpendicular distance of 1.5 feet, right? And this gives us a clockwise moment. So the moment term has a negative sign in front of that. 200 pounds has a perpendicular distance of 3 feet, right? And that also gives us a clockwise moment. So the moment goes in as a negative term in there. You simplify that, we get this. This is identical to this equation number 2 that we got here by the vector method. So what's going on here? Why did we get different equation? Well, either method, either path is correct. There's nothing wrong here. In other words, you could take the moment about any axis. So either one is fundamentally correct. Only problem is that in this equation we ended up having two unknowns, right, instead of one unknown. So that's why I use this instead of this. Alright, so coming back to this, we have three equations, three unknowns. Let's go ahead and solve. My strategy is the following. I'm going to express TA in terms of TC from equation 2, TB in terms of TC from equation 3, and then I'm going to substitute these two equations in equation number 1. Then the equation number 1 would be just in terms of TC, and I can go ahead and solve for that, right? Once I do, I can come back and solve for TA and TB from these equations. So here's TA from equation 2. Here's TB from equation 3. Simplify a little bit as much as possible. Now substitute these into equation number 1. So here it is. Now you can solve for TC and I get a value of 100 pounds from that equation. Now as planned, I go back and use these two equations, equations 4 and 5, in order to evaluate values for TA and TB. So I get 350 pounds for TA and 250 pounds for TB. And we note that these numbers are the same as the one that we got from the scalar method, as the way they are supposed to be.